Hi everyone, welcome to the part 2 of the video, the demo video. So I'll be picking up where I left off. So this slide basically talks about the different steps that was taken in order to get the network in place. Basically the approach that was taken for the network design per se. In interest of the time, I would so these are in line with the way the code was written as well. So I'm going to quickly have a walkthrough of the code, and they should inline tie back to these, and I will just describe that how these both tie back. So I'll quickly go to the notebook that has the code in it. So this is it. And so before we start, I just wanted to mention one important thing. There's a comments that so for anyone who's trying to reproduce this code, we need to note that the test data is not part of the zip file that has been provided, because it crosses the 10 MB restriction that was allowed. So because this is a complicated data set for fashion, this actually crosses about 50 MB of it. So for anyone who needs to reproduce this data, they will need to download it. So, and for that matter, this has been documented in detail as to how do we need to get the data setup done, just to ensure that there is the reproducibility for anyone who's trying to run this program. So I'll quickly show you. So if you see the comments, it says the data setup steps in the report has these instructions, and this is the report that I'll be sending out. And if you see here, there is this section called as data setup, and that'll tell you what are the step-by-step things that I did in order to get the program up and running. This is where you download the data from, and then as you go forward, you should be able to reproduce it without a problem. Again, the section that we need to look is data setup steps. The other thing also that I wanted to mention is, even if you don't do these steps and go through, the program will not fail. You will still be able to go through without any error, and this is because we are using the template of the original MNest data. So which was for handwritten digits. So it would end up running this program for those handwritten digits data instead of the fashion data set. So I just wanted to let everyone know that. So what this does is basically it's importing all the required libraries, and here if you see, we are naming our test data set as fashion MNest variable. And here, as you run this command, you will see that you're not downloading anything, you're basically extracting. So this means that you're not downloading the handwritten data set, you're actually using the data set that you've placed on those folders. Quickly running through this step 2 and these two steps are nothing but you're basically checking the shape of your data set just to make sure they're of the same and stuff like that. So this basically tells you that your training set has 55,000 variable images and 784 cells wide, so basically each representing one cell. And this is basically you creating a dictionary of all the labels and the label names for pictorial purposes later. If you see this command, it's basically calling on to that dictionary that you just created, and what we are doing here is we're randomly picking up an image with number 55, and we getting the label as well for the same image. So as you can see, this this image that we picked up has a label of 6, which is a shirt, and this is the actual image of that data set. As I said earlier, you can see that this is pretty grainy, and that's why it can get a bit challenging for the model to recognize them. This is the same thing, but this is for a sneaker. The label is 7, and you can see the sneaker image. Now this is where we start actually building the network. So going back to the slide here. So the first step is setting the network parameters, and that's what we are doing here. If you see this, so basically what this step does is, this is where we define our structure of the network. We define how many layers do we want, how many neurons each layer would have, and how many classes or categories, and how many samples do we have. If you see here, that's what we are doing. We are saying that the first hidden layer will have 128 neurons. We are saying that the input would have 784 cells. We are saying that the classes is 10. So yeah, as it runs from 0 to 9, so basically that's what we're doing here. The second step, as we go back to the slides again, is creating placeholders. So what we are basically doing here is we are creating like a skeletal structure by giving input as to what's the data structure that we are expecting. So the actual data is not sitting in it yet, but in runtime these placeholders would be used to process the image data. So as you can see, this function accepts an x and y right now and gives you the placeholders x and y, but later in the program, as you run, you will see that nx will go on to have a value of 784 and y will go on to have a value of 10. So to quickly show you that, here you see this nx is nothing but trains.images. So basically the number of your images, shape was, as we saw before, was 28 cross 28. So that's what goes into nx, and that's what will go into ny. The second thing that we're doing here again is the next step is initializing parameters. So here in this step, what we are basically doing is initializing the variables. So again, this is nothing but every layer that we work on, the hidden layers, has its own weights and biases. So in our case, we have it is a three-layered model. So every layer would have a weight and a bias. So that makes about 6 parameters. So what we are doing here is creating those 6 parameters and giving them a starter value, like an initialized value to start with. We need to note that these values are just for initialization purposes. As we start training the model, these values get updated as the training occurs. So if you can see here, the weights are being initialized using the Xavier initialization, versus the biases are initialized using the Zero initializer. You can see that for all the, and then the output of this is basically you're sending back a dictionary which has all the 6 parameters and their values. Next is the forward propagation. We already talked about this. This is where your data transfer happens. This is where your layers are actually talking back to each other, and what we are actually doing is nothing but matrix multiplication. So if you see in this example, here you will see that x is the input that you received, the 724-bit one, and w1 is the weight for the first layer, b1 is the bias for the first layer. What we are doing is basically multiplying these two and with the bias and creating a z1. The z1 then goes into the output of the ReLU function, and that's how you keep going ahead. So just to show you the image again, so this is where z1 is created, then the output of it that goes to this activation function and stuff like that, and keeps going forward. So the final one that you had, the variable that gets created, is z3. Z3 is nothing but the third weight of the third layer getting multiplied with the second output out of the second activation, and that is basically your final output of your forward propagation model. Next comes the cost. So the cost is nothing but this is basically the check where we know how is our model doing. This is where we calculate the variance between what our model predicted versus what was the actual value. So in our case, this is where you will actually take z3. Z3 is nothing but what you got out of your last function, and z3 is what your model gave you. Y is the actual true labels, and that's what you're doing here. You're putting the logits function variable will have your program assigned classes. Labels will have your actual training data, and this is where you're actually finding out how far are we from our right answer versus our calculated answer. This is a final function, model function, where you basically put in everything that you created above, and this is where you start calling all of them that we just talked about. So as you can see here, we set the costs to null because you have nothing to begin with, and here, as we saw already, you start assigning your image data to variables, and you initialize your parameter, you start your forward propagation, you compute your cost. And here, this is where you do back propagation. So basically, what exactly is back propagation? To quickly talk through that is, this is where after you get your cost, you use your cost. If the number is a higher number, you know you're away from your expected value. So this is where you're telling the optimizer that you want to minimize your cost. So basically, this is where you go ahead and change your parameters. So the first run, you would have had certain values for weights and biases. This is where you go back and change the values because the cost isn't right. So this is where you start optimizing your parameter values. And here, just to quickly show, this is where I start writing for the tensor graph. I start building that. Again, during the program, you also mention how many epochs is the number of iterations. So depending on the number of iterations you're planning to run, your program is cutting up the data into mini batches. So each batch goes through the training routine and creates a cost, and then again it goes through the backward propagation. So basically, the last 3 steps here keep getting repeated. The last 3 steps here keep getting repeated until you have. So quickly to show you, this is where you're plotting your graphs for cost. This is where you're plotting your prediction, and then you're printing out the train and test accuracy. So if you see here, this is where I actually pass the test and train data set to my model, and then it spit out each for every epoch the cost. And this, as you can see, the cost has come down drastically as we move towards the last iteration, which is a good thing. And you can see the test accuracy is 88.9%, which is not great, but good to start with, and for the first model, I suppose. Again, as I said here, this was in line with the code that we just walked through. This is the output of the model again that we just saw. And this is the tensor graph that was created out of the TensorBoard program. And as you can see, there are multiple biases. Your B1, B2, B3, W1, W feeding into the slices. And here you can see your mean function and your softmax function. So that's all. Thank you for listening.